and by association, the functioning of the cardiac cycle. Now, this is quite fundamental, particularly on your journey in understanding the way in which we assess, in a broader sense, endurance physiology and aerobic physiology. The role of the myocardium is clearly is fundamental. It's fundamental to that notion of the delivery of O2 to the working muscle, and so we have to understand the role that it plays. Now, we've partly dealt with that in the previous podcast, so if you want to go back and look a little bit more at the basic physiology of the heart and O2 delivery, go and watch the week 1 podcast on cardiovascular physiology. But one of the issues that we face is that quite often, in both athletic and non-athletic population groups, the heart goes wrong. And it goes wrong for a myriad of different reasons. It might be that there is an underlying genetic predisposition. It might be that there is a certain pathology that has developed, or it may even be induced where we through smoking and so on and so forth. Coupled with that, we also know now that there is an increased prevalence, or there seems to be an increased reported prevalence, of cases of, for example, sudden cardiac death, where we know that athletes, really very well trained athletes, are performing exercise and unfortunately die in the middle of exercise due to some kind of limitation in the heart. And so what this has led to on both areas is a need, both at a patient level and in an athletic population group level, to understand much more about the way in which the heart works, both at rest and during exercise, and start to evaluate that to really understand to really understand the way in which the heart functions when it's placed under stress. And to do that, the most common technique that is used is through the use of the ECG, or you may read it in American publications as the EKG, the electrocardiogram. And so we're going to spend a lot of time today in this session addressing the role of the ECG, and then we'll also spend a little bit of time addressing the role of what's called thoracic impedance cardiography as an alternate means for understanding the functioning of the heart. So, what we're going to do? Well, first of all, we're going to try and address the rationale for monitoring the electrical activity of the heart, and this is a fundamental part. In previous sessions, we've dealt with the way the heart acts as a muscle, and we've dealt with the notion of the generation of force when the muscle, in essence, in inverted commas, contracts. Now, that's at the broadest sense, but the key to this is understanding that the whole functioning of the heart is based upon an electrical activity and what is referred to as a wave of excitation. That is the notion that, in essence, a positive discharge of ions transcends down across the heart to generate, in essence, the pumping component. And then there is a repolarization of the heart, where we in essence get a negative discharge, whereby the heart goes into a state of relaxation, and then the process starts again. So fundamentally, the heart is an electronic or electronically evoked structure. And the ECG is designed to assess the changes in the flow of these electrical signals across the heart. And by understanding how the electrical signals across the heart link to different actions or activities of the heart, we can start to understand where limitations may lie. Coupled with that, what we have to understand is what are the limitations to assessing ECG. Now, this is quite important, because if you're going to make a diagnosis using an ECG, and this applies in almost all contexts of this module, if you're going to make a diagnosis or an assessment, you've got to be really certain that the piece of kit that you're using is reliable. It's also got to be valid. And so we can't just take at face value that an ECG is a great piece of kit because it's used in hospitals and it's used in exercise physiology laboratories. We have to understand that in order to get an output from the device, we need to be really certain as to what that signal is, and that signal is reliable. We can't afford to have noise in the signal, particularly when we're making a clinical diagnosis. We're then going to address a bit of stuff to do with actually what can we diagnose? You know, what can we start to see? Now, we could spend an inordinate amount of time I'm covering this as a topic, but we're going to cover some of the key easy wins that you can observe with an ECG trace. Things like ectopic heartbeats, bundle branch block, arrhythmias, and so on. So very obvious responses. And we'll look at those in both an athletic and a non-athletic population group. And then the final thing we're going to do is we're going to consider non-invasive measures of cardiac output and stroke volume. And this is quite important. The ECG doesn't define for us or doesn't identify for us cardiac outputs and cardiac cycles. It merely identifies for us the electrical activity across the heart. It doesn't tell us how big a cardiac output is or stroke volume. It will merely indicate the change in, say, the activity of the left and right ventricles or the AV node and so on and so forth. But in many ways, the other aspect that we need to understand is actually how big the cardiac output is in the associated stroke volume. And to do that, there are a myriad of techniques that exist, everything from CO2 rebreathing techniques and even using Doppler technique and catheterization within the aorta. We're going to look at a non-invasive technique, which is referred to as thoracic impedance cardiography, and why that is useful to us within the field of exercise science.